first of all, I would like to define what I mean low latency. When I say low latency, that means that when each data point, say from the detector comes in, it will be processed without delay. That's what we mean low latency. And when we say real time, it means that if I have a stretch of about 1 second, it should be finished within 1 second. So that means if I want to achieve low latency, we pay attention to algorithm design, because there should not be a delay, accumulation of data, for instance. So when I talk about real time, that means as long as you have enough computing power, you should be able to achieve real time analysis. And my focus will be on low latency part. So first, I'll give an introduction. I want to emphasize on astrophysical motivation and the computational challenges we want to solve. And then I will talk about the current status of low latency search for gravitational waves. And then I will talk about this time domain method we have in mind and its GPU acceleration. At the end, I'll give a conclusion. So I was told I should target non-expert audience, so I apologize to those experts. So what it is gravitational wave? We always say gravitational waves are ripples of space and time that traveled at the speed of light. This is predicted by Einstein in 1916. And mathematically, to the lowest order approximation, this is caused by the acceleration of mass quadrupole moment. So in fact, there's one Nobel Prize that has been given for demonstration of gravitational wave by observing the orbital decay of the binary pulsars. Because when the binary pulsars are orbiting with each other, they are losing energy and angular momentum through the emitting of gravitational waves. Therefore, the orbit will be decaying, and it has been observed that the decay of the orbit is consistent with the prediction. So we divided the gravitational wave sources artificially into 4 classes. The first one is, we call it so-called in-spiral source, or you'll see CBC source. I'm going to use it interchangeably. And these are basically a source from the binary of compact objects like neutron stars and black holes. And waveforms, the in-spiral part of waveform can be calculated using perturbation theory. And then for the merger part, for higher masses, when it's important, people here are using the numerical simulation to calculate waveform. And then this ring-down part, again, can be calculated. So therefore, we consider this part of search will be like with sources with known waveforms. And also the other thing that the duration of the signal will be kind of short, in the sense that for advanced LIGO, it's going to be about 1,000 seconds because of the frequency band. And the second class will be with so-called burst search. Burst means you don't know what you are looking for, but actually we have something in mind. For instance, one thing will be the wave from the asymmetric core collapse of supernovae. So those things that we're thinking about in terms of hundreds of milliseconds, and we think we don't know the waveform. And of course, it should include everything of bursts of short duration. And third class is the continuous wave. These are basically pulsars. Say a pulsar that's a fast-spinning neutron star, say it's not a spherical shape. It has a little mountain on top of it. Because it's fast-spinning, it's emitting gravitational waves. In a sense, it's kind of weak, but it lasts for a long time. You have to integrate the data for months of years in order to detect it. So that's a continuous wave. At the end, the last class is the stochastic background. That means just you have so many sources, they are overlapping, signals are overlapping. So you're not detecting individual sources, you are detecting the background. And that can come from the Big Bang cosmology or come from the populations of astrophysical sources. So what we want is a direct detection of gravitational waves. So what is the observables? What is going to happen is that gravitational wave will cause the length change of a test mass. For instance, as shown here, if you have a ring of free mass, with gravitational wave coming perpendicular to this surface, to the plane, what's going to happen in one dimension is going to stretch and squeeze, and the other dimension going the opposite of squeeze and stretching, as shown in this ring. So what we have designed is an L-shaped interferometer that will detect this effect. So what we do is that we shine a laser using beam splitter. One go down this way and reflected by a mirror. The other beam will go along this line this on and reflected by a mirror, because of the presence of gravitational wave, it will introduce phase difference for these two lasers. Basically, the travel time will be different. So at this end, we'll look at the interference pattern of these two beams of lasers that detect the so-called strain, basically the fractional change in the length. And that is the observable quantity for us, and which is unitless. So we already have laser interferometric gravitational wave detectors in place. And the two sites that's at the US, that's at Hanford, Washington, and the one is basically right here, Livingston. Here's the picture, and there are two detectors at the Hanford site with different arm length. One has a 4-kilometer arm length, one has 2-kilometer arm length. And so there are 3 observatories and 2 sites in the US. And there's one with 600-meter arm length in Germany, and one was in Japan. This is the initial stage. And then there's another one in Virgo that's in Italy, called Virgo in Italy with 3-kilometer arm length. And you'll find that length matters, even though people deny it. You'll find the most sensitive ones are the one with long arm length, the LIGO one and the Virgo. And the status is that these initial gravitational wave detectors are very successful. They have reached or passed the design sensitivity. And also, we have managed to have 3 detectors observing in coincidence with accumulation time of 1 year. And that's a very big demonstration of that we can do the gravitational wave astronomy with all 3 detectors. And the advanced LIGO and Virgo detectors have been funded. And I know that for LIGO, more than 50% of installation has been done. So basically, it's there. It should be operational around 2015. And it should have a 10 times sensitivity improvement than the initial stage. That means about 1,000 times improvement in its detection volume. And the prediction is that tens of detections for, say, neutron star, neutron black hole binaries should be detected per year. Of course, it has uncertainty in it. And therefore, we are expecting the first detection of gravitational waves in the next decade. And the second thing that we should be expecting is that we should detect basically the first electromagnetic counterparts of these gravitational sources. And that's actually the focus of this talk. I shall mention that there is a as I have shown, there's a worldwide array of the gravitational wave detectors. As you see the 2 sites in the US, the LIGO site, they are separated by about 10 milliseconds light flight length. You can see Virgo here, and in Japan, the previous called LCGT, now it's called Kagura, has been funded by about $100 million to build the underground cryogenic detectors there. And then there's a recent development is that LIGO is considering moving 1 copy of the detectors in full length from Hanford to India, and it will be part of LIGO, and that's going to be a new. It looks like they are succeeding in this respect, and it's and I also show one here. And unfortunately, this is a sad story about Australia. So LIGO actually initially offered a detector to be moved to Australia and will be located at Western Australia, and unfortunately, our government is not wise early enough to accept it. So now it's basically going to India. So, it's a bit cut off. So what matters is the baselines, because these baselines, the long baselines means that the wave will arrive at different sites with a time delay. And that information of time delay is crucial to find the source direction. And therefore, longer the baseline, the better. And I should mention that the 3rd generation gravitational wave detectors is also in planning. This is the fancy Einstein telescope that's planned in Europe, and it's going to be underground with a triangular shape, and with its cryogenic. That will have 10 times better sensitivity, even than the advanced LIGO, and with lower frequency range, a few hertz. And they will start this construction only after the first gravitational wave is detected. So therefore, the timeline is like the mid of 20 years. And of course, we also have space gravitational wave detectors for lower frequencies. And now we have because most of you might have heard about the NASA ESA space program, LISA, which is basically doomed. There's no fun for it. So now Europeans are proposed this ELISA. E means evolve, not European. I think it also means European. Anyway, so that's the future, but it's far, far in the future. Okay, so now I'll talk about gravitational wave data analysis. Basically, we have globally distributed researchers all over the world. Yeah, we have large community, about 800, more than 800 people. We have many computer scientists, many astronomers, relativists, engineers, and physicists. And we have computer resources also globally distributed. We use great computing for now, and data will be copied to several sites. Okay, this is just a very old list of all the members, very old one. And you can see the Caltech, places like Caltech, MIT, and Max Planck play an important role here. And then all the sites like LSU and the Hanford site, and then places like UWM. And I shall mention that the physics professor, Agabi Gonzalez, here has been elected as the spokesperson and will be in term for the next 2 years. Okay, so what about gravitational wave data analysis? We actually have no problem with data rate. We have a very manageable data rate, about a sampling rate of 16 kilohertz, so it's not a problem. But however, we often need to search large parameter space, so that therefore it will be computational intensive. And we'll be searching year-longs of data when the detector is running for more than 3 or more detectors. And for the best result, we should combine data from different detectors optimally and for the best detection and for localization, especially for localization. And these detectors will be oriented in different continents. So here is the focus of, we call it Compact Binary Coalescences, CBC, or in spiral source. So as I said, these are going to be chip-like signals. Why do I call it chip-like? Because with time goes on, this is basically the last stage before the merger of, say, 2 neutron stars, or a neutron star, a black hole, or 2 black holes. That's the last stage. In a sense, the frequency will increase monotonically, with the amplitude also increase monotonically, and it will be in audio band. If you play it in your audio band, you hear the sound just like bird chirping. And the frequency range is about, for the advanced detector, it's going to be between 10 and 2 kilohertz. 10 hertz to 2 kilohertz, and duration for the typical neutron star masses will be about 1,000 seconds. Basically, in my opinion, ground-based detectors are designed to detect these sources. And we, as I said, we expect to see tens of detections per year. Because we know the waveform of this kind of sources, the optimal way to detect this source is to correlate the waveform with detector. So what you can do so far is that you actually use the FFTs, fast Fourier transforms, to do it just because it's more efficient. So you correlate the data with the templates and weight it by noise. The only problem is that you need to, because you have a mass range to search for, you don't want to miss the signals. So there's a very large template space you should cover. And for initial LIGO, for thousands of templates, we basically to search through it with 97% overlap, means you recover the optimal signal to noise ratio. We need about more than 100 CPUs just to catch up with the time, say, meaning real time. And then for the initial design there, because we use FFTs, that means you need to accumulate data long enough before you do the FFTs. That means the data comes in, it will wait for a long time before it can be done. That's a long latency. And we basically saying that we need new algorithm to have low latency data. And the other thing is that so far we did not do optimal detection with respect to each sky direction. Actually, the best way will be for each sky direction, we combine the data and do the coherent analysis. That's the most sensitive detection method. But if you add that to it, it will add another factor of 1,000 more computation to it. So for advanced LIGO, you have more templates. Hundreds depends on mass range, and the overlay hundreds, thousand times more. And then for sky direction, will have more. So you do need a lot of CPU to catch up with it. For now, I'm going to talk a little bit about astrophysical motivation. Why do we care about low latency? And why do we care about real time? Why even use GPUs? So before I go into details, I just want to make a few points I want to make. First of all, we would like to be part of the effort in detecting the first gravitational waves. And secondly, we want to be part of the effort to detect the first basically electromagnetic counterparts of the gravitational wave sources. And I want to argue that low latency detection or the early detection of these inside spiral sources is probably the best bet you can have to confirm the association of the neutron star, or neutron star black hole binaries, confirm the association of these with the so-called short gamma ray burst, which I shall explain. And this will be another revolutionary discovery if you can confirm this association. Of course, if you can detect signals as soon as possible, you always have better chance to catch the electromagnetic counterparts at its higher signal-to-noise ratio or the early stage related to the engine. And the other point I just want to make quickly is the angular resolution is the key, because what we want is to provide triggers and a sky direction to the, say, optical telescope, saying, look, go and look for that direction. We have found some source there. So, but you need to have a very small angular size for them in order for them to see it effectively. And therefore, that's why you can see that people are trying to move detector to Australia or to India just to have a better angular resolution. And having an efficient code is also good for, say, public outreach, and for in the future when LIGO data become public, and that's also another bonus. Now I'm just going to extend the points I want to make here. I think one of the most exciting thing, what we would like to be involved is to confirm the association of the binary neutron star, or neutron black hole binaries with the short gamma ray burst. So short gamma ray, we know gamma ray bursts that have been detected. You know, this is like 35 years of mystery. It has been detected basically at the rate of 1 per day. But they are more or less, they sort of classify into two classes. One is so-called long gamma ray bursts, one short ones. And short ones have, so if you look at the grouping, is that the duration of the gamma ray emission is less than 2 seconds. It could be milliseconds, tens of milliseconds. And people were always wondering what is the origin of this short gamma ray burst. Because these are very short bursts, it's very hard to find its other counterpart, like in optical and X-rays. And in 2005, that's the first breakthrough, and this is the news from NASA. Basically, we have solved a 35-year-old mystery, and we don't see supernova associated with it. Therefore, it's not due to the collapse of massive stars. And they found evidence are consistent with the fact, with the thought it comes from the merger of the binary stars, binary of compact objects. Actually, I have a movie here to show, but I think I'll skip that one because it doesn't work. So, and then just last year, you can see the news again. They said, okay, cause of short gamma ray burst determined, because this is again the AEI group. They actually simulate numerically of the last phase of neutron star binaries and see them merge. And within split of seconds, you see the time scale. Oh, we cannot see it here. Basically, within milliseconds, you'll see that they merge. And there will be some kind of accreting process, and then you can see, because of magnetic field, you'll see a jet line, jets rushing out. And this all happened within seconds after the merger. Now remember, before this merger, we should have been detecting, if they are close enough, we should be detecting gravitational waves. Therefore, gravitational wave will be before the merger, lasting about 1,000 seconds. And then basically immediately after the merge, you should have this jets, accretion thing, and then jets, and then it will give some kind of prompt emission in gamma rays or X-rays, even radio, according to the theory. And then there should be, and this jet will run into the interstellar median, and that will cause have the so-called aftergrowths. Also in X-rays, optical, and radio, but you can see the intensity will be going down quickly. Here is basically, for the long gamma ray bursts, these are well observed. They have seen the prompt emission, not in radio, but they have seen prompt emission basically in X-ray. Gamma ray itself is prompt, and then in X-rays, in optical. And then they have seen aftergrowth, basically days after the gamma ray burst itself. But the theory is that for the short gamma ray burst, this part should be similar, just with smaller energy scale. That means we should be see prompt optical emission, and we should see optical afterglow right after the merge. And you can see the observation, because these bursts are so short, Therefore, and the main detector that's providing triggers are Swift. By the time Swift gave the signal saying, go and look for that direction, it's too late. You basically, the earliest observation is after basically something like hundreds of seconds. So we missed this part. Now, what I'm saying is that in fact, in the future, the best candidate, best bet will be we use gravitational wave triggers to provide the event, ask the optical telescope to look for these events. And once you can detect the close approximation of association of gravitational waves and these prompt emission and afterglow, you can say firmly now, finally, it's not from the numerical simulation, not from the observation, you guesswork from observation, you really associate these two events together. And I think that will be a breakthrough in astronomy. So basically that's the proposal. The other thing is that Swift, even though Swift might still be running for advanced LIGO time, but if you look at the data of Swift, you'll find that it almost found nothing within the LIGO horizon. This is because gamma ray, in the beginning phase of gamma ray burst, those gamma rays or X-ray, they're highly beamed. So it's very hard, even for Swift, to find it. It's a very small chance. But gravitational wave emission will be much more isotropic. You will have better chance. And I also should mention that, so we have, for advanced, in 5 years' time, we should have advanced detectors. And we should have Fermi, that's a gamma ray all-sky monitor that'll be looking for this part. And we have ground-based robotic telescope. Those are optical telescope. They can swing to the sky direction at request at about within 10 seconds. Then we'll have Swarm. This is basically new Swift. But I said they might have problem detecting any of these gamma ray bursts within our LIGO horizon. And then we should have the PTF and LSST and pan-stars. These are the wide field optical telescope. Because as I said, gravitational wave detectors are not so good with localization before it becomes better. At this time, typical angular resolution will be like 15 square degrees. That's huge. So you don't need wide field cameras to do the follow-up work. And then, as I said, the radio emission will come from much later, can be years or time. And then we have Meerkat, that's basically the SKA, square kilometer array pathfinder in South Africa, and SCAP, that is the SKA pathfinder in Australia. And we should also have EVLA, which is very sensitive, that they can do the follow-up work. So actually, it has a very good promise. So yeah, I think this is just a summary of it. So basically, my point is, I think gravitational wave detection, do it as soon as possible, will help basically set up association. It might be the only chance because the other satellite won't be working, and then we don't know any X-ray detectors. Let me talk. Of course, the community realized the importance of low latency search. So here is a timeline. Basically, we just have the last S6. Science run 6, and then starting from engineering run, we don't have data anymore because we're doing the upgrading. Engineering run first, engineering just ended last month. So what they are doing is that they are trying to testing the low latency data transfer. First of data should be transferred to the computers with low latency, and they have done so for the first one. And all the low latency data at this moment will be sent to Caltech because of I think the good link between Caltech and the Virgo, the Italians. Detector. And for LIGO, the latency is about 4 seconds to get data to Caltech. Not because of fundamental difference, but just because that's the design. They said if you need it, it can be lower, and Virgo is higher. And there are also preparations of sending the triggers around for, say, optical telescopes. There are 2 pipelines, low latency pipelines. They are all in the frequency domain, meaning that they use the overlapping FFT method, basically, to do the that has participated in this engineering run. And the first one is called GSTL in spiral. It's about 30 to 80 second latency. And MBTA, that's by the Virgo collaboration. It's about 250 second latency. But as I showed that, in fact, we need lower because remember that the prompt emission comes basically right after the merger. So that part, if you have this low latency, you might still miss the prompt emission part. So in the last few minutes, Yeah, I should mention this. Yes. So for MBTA, these are basically French, two French, Benoit. I don't know if you know him, and I think Michel.
No, I mean, what physical process will contribute to the latency? It's certainly not speed of light. Something else.
Oh yes. Okay. So what causes once the data transfer, that's about 4 seconds, and then you need to do say whitening. So that's again you can make it almost zero latency if you use some kind of IR filter base. But right now they just do the overlapping FFT. For FFT you have to accumulate data and do the overlapping that contribute to the latency. And then for their pipeline, because it is frequency domain method, it's again overlapping FFT. So that's another few seconds. And then you say, okay, well, now we need to compare all the output signal to noise ratio to see which one is above the threshold. But it's okay, maybe we don't care about that much about latency. We accumulate data first and we do something, and that's another about 10 seconds latency. And then you say, okay, we look at all the database to see if coincidence. And then it's maybe for when you don't care, then you say, okay, another 10-second latency in it. So it goes like this. And then there's another thing, is it has to go into a database. That's another few seconds. So accumulative is about the best one is 30 to 80s. And MBTA, they only have 3 frequency bands. So they said, well, we don't need it. We don't need low latency now. So they just do a 3-band frequency band overlapping. So that means longer latency. So these are the, nothing is fundamental. So, but you have to give a good justification to get really low latency, and that's what we are aiming at. So our effort is actually a time domain method. I'll go, because I did not intend to discuss the details here, but I just want to say the people here is that we are actually a large collaboration, and then we will be locating at University of Western Australia 2 faculty members, 2 students, and 2 computing staff. That's not enough. So we are collaborating mainly with the Caltech group and their derivative, because these people, for instance, from the Chad and Cape, they are from Canada, and Drew from Max Planck Institute. And we are working with theorists from Caltech as well for Jan Bay's group, that he's on the theory of the method, and we are working the pipeline implementation with those that were postdocs from data analysis group from Caltech. And for our GPU effort, we are working with Professor Du's group and his student, and they are the main working force, and we are hoping to recruit more from here. So as said, our motivation is to provide really extremely low latency. Just every data point comes in, it should be analyzed. And the algorithm we have proposed is very simple. It's embarrassingly simple in the sense that, so because this is the wave, and we sort of divide it into segments, and for each segment we put one filter. And this filter, Y should be the output signal to noise ratio. X should be the data points that comes in. So the output of the signal to noise ratio should be a linear combination of the new data points with the previous output. And this is one filter corresponding to one frequency band or a one-time segment, because they are corresponding to each other. And mathematically, you'll find that this is equivalent to correlate this segment of data with the sinusoids of fixed frequency with exponential increased amplitude. Mathematically, you can show that. So therefore, for initial LIGO, we need about 200 filters. And you can see the computation is really simple, just 2 multiplication and 1 addition. And so what we need is to design the coefficients. And it looks very simple, but I have to tell you the designing of a stable and correct IR filter is not trivial. And this is like the one we actually prove that it's correct and stable. So what we have done is that we have done a theoretical study and numerical study to show that we can recover up to 99% of optimal signal to noise ratio, and we can use multi-band, because it's multi-band, you can use multi-rate processing, and it should be more efficient with the time domain direct correlation, so-called FIR, finite impulse response method, just direct correlation. It should be much faster than that, and it also should be faster than the overlapping FFT method when the latency is low. So for advanced LIGO, we should be faster for latency less than 20 to 200 seconds, depends on the technique you use in it. And for ET, it should be longer latency. That means we should be faster, even we can beat the frequency domain method. The other thing is that because all the other methods were scaled with the duration of the signals, everything, and number of templates. So what we've shown is that our computational cost will remain almost the same for compared to initial LIGO, should remain almost the same as advanced LIGO. For advanced LIGO or Einstein telescope, even though the frequency band is lower, you need more templates because it's so simple, and because they are extending to lower frequencies, you don't need more filters to filter lower frequency part because they are basically sinusoids. And within a factor of 2, but these are all, of course, all theoretical values. And I should point out, we do have 2 papers. One is a theory paper arguing on these points online, and the other is more like numerical test to see, indeed we can retrieve that many, the optimal signal-noise ratio, and also our GPU paper is going to be submitted soon. I think I just have 1 more minute, probably. Basically, what we have done is we have implemented the pipeline. That means we can take the detector data, we can do the conditioning, and we apply the search engine, then we put the event analyzer. That has been applied to the detector data. And that is, in the SQL, it has been done using so-called GStreamer. And then we have the GPU accelerated engine that has been developed as well. The only thing that's missing is the interface, of course, and a lot of testing on it. And this is what we are doing right now. So this is just a status, meaning we have done this multiple band, multi-rate approaches, and we also have proposed the template interpolation to make number of templates smaller, and we tested on 40,000 S5. That's a real detector data, and with signal injection, we can correctly recover all the signals that we should be recovering, just like an optimal method. And the GPU acceleration has been done. We can basically process 5,000 templates in real time with 1 second latency. And we can show that it's about 50 times faster than the CPU implementation, and we tested the accuracy. So we are doing more for advanced LIGO because the number of filters will be a bit different, and we are implementing all the downsampling, upsampling technique, and we are implementing the interface. Okay. Last slide. In conclusion, so we are entering a new era for gravitational wave astronomy. There will be lots of discoveries. There are computational challenges, and then we are developing the low latency pipeline to give the gravitational wave triggers as soon as possible, and if possible before the merger even, because the signal to noise ratio will accumulate with time. I think this will probably the best bet to firmly establish the neutron star, and neutron black hole binary association with the short gamma ray burst, and that will be another breakthrough in astronomy. We think the GPU acceleration will play an important role to make it real time, to make it efficient, and we do need help from the computing community. Thank you. Yeah, so it's closely associated with the policy, right, of where the data is going to be. So for the C pipelines, we use the, say, Caltech clusters or UWM clusters. Those are, basically, we have access to all computing clusters belong to LIGO, basically. But if low latency data is only going to be copied to Caltech, we'll be using Caltech clusters. However, we are in the process of applying the data to be copied to Australia in real time. Then we can use our local computer clusters. In fact, we actually we have this new $80 million policy center set up because of our bid for the SK. I don't know how many of you heard of it, but we are bidding against South Africa to host the $2 billion SK project, the radio astronomy project. So we got this computing center, and 75% of the time can be used for other part of astronomy, and we have the support from policy centers. So there is a possibility to do it in Australia, but it will depend on the policy. Yeah, 4 seconds. That's purely because they just do it this way without considering lower. It's not fundamental latency. It's more like they package. They put data in a package, right? And with 4 second accumulation time, that's just say, okay, they say, okay, we can do sub-seconds if you can give me a good justification. Yeah, so there's no fundamental problem in the latency here.
Makes sense to have the detection, the pipeline
that's why I would think LSU is a very good place for it, because you have the detector right there, you have the computing center here, and you will have the GPU clusters. But yeah, okay, there are a few things. One thing is you can do that, right? At each detector site, you have something fast. That does not take up too much computational resource, because the site have lots of things they have to send out data and everything. But there's one little thing is that in order to give the sky directions, you need the data from all sites. So you still need the data to be copied in low latency to the sites, from Italy, for instance, and from the other sites. And that basically it will be the same kind of latency you are going to experience in Caltech, because they are also waiting for all data to come in. So from that point of view, you might need, maybe Caltech is fine. But on the other hand, I think what you can do is do less, saying you detect at each site, right, quickly, and then you exchange information like time, merger time, and look at the time delay and sort of get a sky direction already. That will be very fast. That means you cannot do it optimally, but you can do something really fast. So I do think it's a good idea to do locally.
I can imagine that you have something locally which cannot correlate with the others, because but then it might trigger something, and then it might just have a short burst of information going out to
yeah. I mean, I'll go for this, because I think you guys are in a very good position for it. But I mean, yeah. So that's basically you need to make the case, like everything evolved, like it's sort of democratically. You make the case, and then you say, okay, then they'll consider. There's nothing is fixed. Their first cut saying, okay, everything go to Caltech because they want to protect the bandwidth. Basically detect and make sure the data can go in and out without problem. No, first thing has nothing to do with bandwidth. It's with the way they pack the data. Yeah. Arbitrary. Yeah, arbitrary. It probably has something to do with the entire mechanism, but I think it's almost arbitrary. I mean, I was talking to them like, can you do sub-second? They said, yes, we can do it. Give me a justification. And demonstrate your pipeline really works, and there's a good. I think astrophysical motivation is very clear to me. You just want. I mean, forget about the real example. You just want something as soon as possible. So, yeah. But no, I have been promised if I give a justification, they'll do it. It's not a problem. But the other thing is, of course, I did not mention is on the site you need to do detector characterization. You need to know how your data behave, and that should be done at low latency at the site as well. And that's actually what is going to be tested in the next engineering run. So you can see everything is converged. Like 2 years ago when we talked about low latency, everybody said, why do we need it? But now everyone, everything is going towards this direction. Yeah. Any, yes?
So you have a slide that says that the chirp form can be represented by a sum of constant frequency sine waves, each with an amplitude and an exponential
Mm-hmm.
dependence. Is the coefficient is the exponent in the exponential related to that envelope chirp time?
Yes. Yes. So we basically have to design. So remember I think that's the slides for the only mathematics that's shown here. Yeah. So that is reflected in the coefficients. So this coefficient will be chosen such that they closely represent the waveform. First of all, if you look at mathematics, the mathematical solution is that there's going to be a sinusoid with fixed frequency of exponentially increasing amplitude. But then you will say, okay, how well does it match to the waveform? And then do some Taylor expansion. You say, okay, I will choose this coefficient such that the second order error is less than this fraction. So that's basically folded in within the coefficient design. But the reason that it works is that because for this in spiral phase, we have this so-called stationary phase approximation that's actually currently in use in the sense that locally for each reasonable segment time, it's basically sinusoid with phase frequency and then slowly increasing amplitude. That's the reason why this method actually works. So if we go to the merger phase or the rain down, we are not sure. so that's given. It's a coincidence because the designing of the IR filter is not so simple, but somehow it works because there's a reason, because the waveform itself has this property. Yep. Any more questions?
The data you have, is that single position data, or you have to use double position data?
Yeah, so for C code, it can be double precision, but I think at this moment we use single precision. But for GPU, if you use double precision, your efficiency goes down by a factor of 2. But we still have 3 or 4 years. So
single position is good enough for the data?
yes, yes, for now it's good enough, yeah.
Will it also be good enough when you need more templates for the texture?
Yeah, apparently. So far we are actually using the single precision, so we are not. That's why people are saying GPU, in the beginning, GPU only works for single precision. Is there a problem? No, because that's what we do. So, yeah, but I think probably there are reasons to use double precision, but I have not seen it yet for now, yeah. Yeah?
How do you choose the number of these tokens you use? Choose a large number to approximate, right?
Yeah, those are technical details I have hidden. That's hidden. So basically, one way you can do it is do some optimization, right? You have a few parameters, and you say, I take a derivative of the overlap, and I get it. So what we did is, we did something. We say, okay, we take a few segments, and we calculate overlap, basically the fraction of SNR. And we say, okay, in the beginning, we just choose a few parameters, and it worked. But of course, we look at the Taylor expansion, second order, look at second order error, saying I impose that the error should be less than this and that, and I choose a few parameters. And then we just choose something by hand. No, that actually gave me the overlap. So it's like ad hoc parameters before we even try to do the optimization. It gave us 99% overlap, so we just don't do anything more. So I can tell you, so with this, I think with the parameter we have chosen, I think the segment is related to how you do the second order error related to the approximation. And then I think for initial LIGO, it's about 200 of them. For advanced line, it's about 600 for the 1.4, 1.4 surround mass. But we have not done anything fancy, if that's what you are wondering. Yep. Yep, any other questions? Well, thank you. I think this talk will prepare you for the next talk. Because it's, yeah. Yeah.